Good morning to everyone. I am ManjuBhashini, M.Sc B.Ed, Assistant Professor and Head of Department of Mathematics. I am going to share few points about linear algebra. First of all, we are going to see applications of vector spaces. Vector spaces are also used in the machine learning, and their various other uses are data representation, represent the image, text and numerical data sets, has vectors in n-dimensional space. Next, machine learning and data analysis use PCA and SVD and similar methods for dimensionality reduction and clustering and pattern discovery. Feature of vectors create engineered feature representation where each dimension corresponds to a measurable attribute for model input. Vector operations in algorithms perform addition, subtraction, dot product and norms for a task like similarly search or centroid computation. And search engines finally represent documents as vectors in high dimensional word space to measure similarity and relevance. Next, we are going to see the definition of vector space and space. Vector space is nothing but over a field F is non-empty set V together with a binary operation and a binary function satisfy the 8 axioms listed below. In this content, the element of V are commonly called vectors and the elements of F are called scalars. Here, associative of vector addition, we know associative property. Already we studied in group theory. So, those axioms also should satisfied by the vectors. So, axioms of vector addition, associativity property and commutativity and identity and inverse of vector addition and compatibility of scalar multiplication with the field multiplication and identity element of scalar multiplication and distribution of scalar multiplication with respect to vector addition and distributivity of scalar multiplication with respect to field addition. So these properties are defined here. So if these properties are satisfied, axioms are satisfied, then we can say that V is a vector space over the field F. Secondly, we are going to see the definition of subspace. Definition: a subset W of a vector space V over the field F is called a subspace of V if V is a vector space over F with the operation of addition and scalar multiplication defined on V. In any vector space, note that V and null set are subspaces. Latter is called a zero space of V. Here, the following axiom should be satisfied to be a vector should be V or W should be a subspace of a vector space. X plus Y belongs to capital W whenever X belongs to W and Y belongs to W. So it is closed under addition. Next, C into X belongs to W where C is nothing but element from field and Z X belongs to vector space, vector V. V is closed under scalar multiplication. Next, V has a zero vector is nothing but 0 plus V is equal to V. Like that identity property should be satisfied. Each vector in W has an additive inverse of W. If these four axioms are satisfied, then we can say that set W is a subspace of a vector space. Next, we are going to see the linear combination. If V is a vector, it's called a linear combination of vectors V1, V2, etc. Vn. If it can be written as V is equal to C1 into V1 plus C2 into V2 plus etc. C2 into Cn into Vn, where the C1, C2, C3 up to etc. Cn are scalars. Example, we have to take the two vectors V1 and V2, and here V is equal to 1 comma 2 and V2 is equal to 3 comma 1. We have to check 7 comma 5 is a linear combination of the above two vectors. Find C1 and C2 scalars, then such that C1 into 1 comma 2 V1 plus C2 into 3 comma 1 equal to 7 comma 5. So we can get C1 plus C3 C2 is equal to 7, 2C1 plus C2 is equal to 5. By solving these two equations, we can get the answer C1 is equal to 2 and C2 is equal to 1. So If you apply that on the right hand side of the equation, we can get the answer 7 comma 5 is equal to 2 into 1 comma 2 plus 1 into 3 comma 1. Since we can get 7 comma 5 on the right hand side, here we can conclude that V is a linear combination of V1 and V2. Next we are going to check linear span. Linear span is nothing but it's a set of a linear combination of all these vectors. Span of v1, v2, etc. vk can be written as c1 v1 plus c2 v2, etc. ck vk. So span of v1, v2, etc. vk can be written as c1 v1 plus c2 v2 plus c etc. ck vk. It describes all possible vectors you can form using them. Example, v1 1 comma 0, v2 0 comma 1 in r2. R2 is nothing but second two dimension of real line. Span of v1 comma v2 is nothing but r2, because any vectors x comma y can be written as x comma y is equal to x into 1 comma 0 plus y into 0 comma 1. Thus the span is entire plane. Next we are going to check linear dependence. The set of all vectors v1, v2, etc. vk is linearly dependent if at least one or one non-zero linear combination gives the zero vector c1 v1 plus c2 v2, etc. ck vk is equal to 0 with not all ci is equal to 0. Equivalently, one vector can be written as a combination of others. Example, here two vectors are given. Check the dependent condition. If these two, so 2 into 1 comma 2 minus 1 into 2 comma 4, which is equal to 0 comma 0. The non-zero coefficient exists 2 comma minus 1. So they are linearly dependent. So this is how we have to identify that the two vectors are linearly independent or dependent. Here we can write v2 is equal to 2 times of v1. Next we are going to check linearly dependence. Vectors are linearly independent if the only linear combination giving the zero vector is the trivial one. So c1 is equal to c2 is equal to etc. ck is equal to 0. No vector can be written using the others. So v1 and v2, here we can take the constant c1 and c2 is equal to 0, so that term v1 is equal to 0. So we can't write one vector into product of the scalar product of the another vector. So we can say it is linearly independent. Next we have to go that basis of the vector. Basis of the vector space is a set of vectors that satisfies two conditions, linearly independent and span the entire space. If these two conditions satisfied, then we can say the vector space is a basis of the term. Basis is equal to minimum set of vectors that can generate the space. We have an example in R2, E1, E2. There are the two vectors. These two vectors are linearly independent and span R power 2. So 1 comma 0 and 0 comma 1 is a basis of R2. Next one, dimension. The dimension of a vector space is the number of vectors in any base that space. Example, R2 is a basis, has two vectors, so dimension 2. Such a way that R3 basis has three vectors, its dimension is 3. Then the span of one vector, we can take v is equal to 2 comma 6 and the span of v is a line through the origin, so its dimension is 1. Such a way that we can find the dimension of the vector. Next we are going to see linear transformation. A linear transformation T defined v to v w so satisfies the following condition. One is additivity, T of u plus v is equal to T of u plus T of v. Second one, homogeneity, T of cu is equal to c into T of u for all the vectors u comma v and c is a scalar. We can see in an example, example 1, scaling transformation. So we can take T defined R2 to R2. Defined from R2 to R2, be defined as T of x comma y is equal to 2x comma 2y. So we have to check the linearity first. So T of u comma v is equal to 2 into u plus v is equal to 2u plus 2v. So we can write that as T of u plus T of v. T of cu is equal to 2 into c of u, which is equal to c constant, take outside 2, c into 2u. 2u is nothing but T of u. So T is satisfied these two, additive and homogeneity. So we can say T is a linear. Such a way I have given one more example for the differentiation function. Next we have to check null space and range. Definition of null space is nothing but T defined V to W is a set. So null of T is equal to the vector V. V belongs to capital V, the vector space, such that T of V is equal to 0. Such a way we can write, then this is called a null space. It contains all the vectors mapped to the 0 vector. So say example for that. Let us take T of x comma y comma ez is equal to x plus y plus ez. As per definition, this x plus y plus z is equal to 0. Then we can say it is a null space. A basis for null space is 1 minus 1 0 and 1 0 minus 1. So the null space is a plane in R power 3. Thank you.